Alright, well, welcome everybody to another live stream. Hopefully it's all working. I'm starting to live stream a lot more. I'm starting to actually like it. It's really good. Yeah, I have gotten the live stream up and running, and if you have the title, hopefully this is all working. But as the title suggests, we are going to be putting the we're going to keep emulating the Game Boy, and we're going to be doing some CPU instructions or assembly instructions, whatever you like to call it. I also did a bunch of research, or as much as research as you can do in 24 hours, basically. And I have realized that this is not the boot up. This is the logo, the Nintendo logo that plays when the Game Boy goes down. So this is actually not the right thing. I mean, we put it in the correct memory address. It's just that we didn't get the actual boot up. This is just the logo, and it's not going to run anything. This is actually for the tile set, the tile data that is in the boot up. So I actually have to go look out for that boot data. I don't know where that is, but I have to find it. And I was also looking for like a 2D renderer because OpenGL is a bit more complicated to get 2D out there, so that may be there for later projects. So I was looking at my old code, and I found this 2D game engine, which uses Java Swing, which is Java's built-in graphics and window and all that stuff. However, I don't think I'm going to be using it anytime soon because I'd rather have the CPU done and pass all the tests or whatever. The first thing we're going to do is we're actually going to get rid of this boot up because this is the wrong one. Or we're not going to be getting rid of it, but we're going to be changing it to the correct one. Let's actually look for that. So, if you haven't noticed, I'm actually back where I usually record, so there's not really much of an echo. But I still can't find my mic. I'm really scared. I've packed it up, and it is nowhere close to where I think it is. I guess that's not okay. But let's just continue on. So I'm going to be trying to look for the Game Boy, look up, or Game Boy BIOS ROM. The boot ROM. Here we go. I think this is it. Is this it? Hopefully you said. So I guess this is it. Let's go to the downloads. I would say this is free to get because it's just the boot ROM. I don't think that's going to be much of an issue to get because you can't really buy a boot ROM. This isn't really pirating. And I'm using it to actually make my emulator, and I mean everything on the site is probably not legal, so I don't want you to have any notifications. Where's the... Yeah, so like if I want any of this, I'm probably gonna have to pirate that, but I'm not, so we're good. Where's the download link? Does it down? It didn't download. This game is unavailable. Oh, shoot. Dang it. MU Paradise does not have the ROM anymore. because it has actually got cracked down. Oof. That is a big oof on. That is big oof. Well, hopefully WowRoms has it. I don't. I mean, it looks like it has. No cover. Yeah, I guess it works. And I do have an emulator that actually does work. So download will start in a couple seconds. It's about to. Download ROM. Here we go. So here is our boot ROM right here. I'm actually just going to say Game Boy Emulator Online. So this is probably illegal. You probably can't do this. Yeah, you definitely can't do that. I just wanna play the emulator. I don't wanna Game Boy Advance. Yeah, it's also probably illegal. Man, I'm just trying to find out like an emulator. Oh, well, I gotta get my Game Boy emulator up. Game Boy emulator, no. What is it called? What did I download? GB. It's called GB? That's a gigabyte. I'm just trying to figure out where my emulator is. I don't want to download an emulator just to test this. This is 256 bytes. It hopefully is. Yeah, 256 right there. So I am going to shrink you down and just put you on my desktop. And there we go. So this, and I'm just going to open it up using probably Sublime Text because that can open up ROMs. Open Sublime Text. Always used to open GB files. Alright, let's see what we got. We got ourselves a bit of data right here. This is not in the format I want. I wanted it to be like spaced off by bytes. But what can you do? So this is our boot ROM that has to go at the beginning of our emulator. So this is what we gotta basically load to ROM with. And so let's do that. Let's go in here and put this in boot up. 1, 2, 3. Oh, that worked. Boom, 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 and boom. So I actually don't want any. I don't want any of this. I just want plain old. Just some simple boot code. So once I get this to work, holy crap, I would be in the good. And I probably won't have everything done by then. I just want to see if the CPU can run this. So thank you, you won't be needed anymore. I wonder where the character data is. I forgot what the startup was, and this actually needs to go to the beginning. So this actually is at the beginning, 256 bytes of the ROM. So it goes from 0 to 0FF, or 00FF. But I'm just saying that because that's the same thing. So this should, in theoretical work. So if I go to main and I just read the first byte, I should see an error. I know I'm going to see an error. Because this is the first byte and it's only supposed to be 31, and in fact it is 12,000 or 31, whatever that is in hex. So it's split by this and then it is converted. So I had to actually split this, and then so for each one times 2, and then I plus equals 2. And then now we can do the same thing. Parts, bytes, dot split. I can't really split my substring. I think that's right. I think that's right. Okay, so substring, we want it to begin at that, and then we want it to go to 2, and then the second one is just going to go from 2 onwards. This has got to move to I plus 1. Alright, so right, that won't work. We just have to. Okay, so this goes to the entire bytes. Start plus bytes will go from 2 to 256. Then I times 2, and then I times 2 plus 1. And that should load whatever 31. Okay, 31 hex to decimal. So 31 is 1F, so it should, or 31, no, the other way. I want it 31 hex to decimal, like I want that. And then 31, convert. 49, so 49 should go in the first one, and it does. Alright, so that should be working right there. Just had to do a bit of fixing. So here's the boot ROM that goes to the beginning, and I want the emulator to run this probably by the end of today. And hopefully I have enough time to put all those instructions in. So, yeah, there we go. We got one error fixed. I'm actually pretty happy with how I handled this right now, because all I'm doing, because everything I have in the CPU is so far right. I have all the registers pair up to the next one, and then I didn't really go farther than that. So what are you gonna do? So now that I have that fixed, we can actually start putting instructions in, and that is actually going to be really cool but really boring at the same time, because a lot of them are going to be the same instruction except as a different like parameter. So yeah, I'm probably just going to have a separate class called opcodes. New class opcodes, and this is just going to have all the opcodes in it. And so let's create public opcodes, and there we go. So how many instructions does it have? And this is going to have a CPU, and it's going to keep that. So private CPU, and then CPU is equal to new, or is equal to CPU, or this dot CPU is equal to this. This dot CPU is equal to CPU. So what that does is it's basically, we can now implement all the opcodes in here by doing private opcodes. Just say ops, and that's equal, we'll do that in the constructor. Ops is equal to new opcodes, and then we can put this as the CPU. And so that way it can actually access all the registers and the program counter and all that. So that should be good. And basically, and that's good because the CPU Oh crap, the CPU can't read or write anything to memory. Memory, see, it should be able to read or write as well. And it can't do that. Only the Game Boy can do that. CPU attach memory. CPU private memory and then we just import memory, and then we can just put the memory, or we could say attach memory. Public void attach memory, just in case, because maybe the memory is going to be different. And then this can be memory mem, and just say this dot mem this dot meme is equal to mem. So now we should be able to read and write, but before we should actually, where is it? Game Boy. And then we need to do CPU.attach memory mem, and then load the boot up ROM. And so, yeah. Now I think we're going to be able to actually do some instructions. So I'm just going to have it all as a function, and then in here, and then like have a little call table to so say we just read byte, where is it? We just read byte 06. Well, we can actually load that instruction into that, like we could just load the function and then call it. And so we can actually do that really good. So we have ourselves this, so we just have load the value of whatever register this is, or whatever the value is next to it, into the register. So we can start doing that. So public void load b, and then just that grabs CPU dot get register BC dot set register 1. Ooh, how are we going to get the next value? If I have to get this, because it has two parameters. It has the byte right after it, and that's going to be loaded into B. So how are we going to get that? We also need to do cycles as well, because it has eight cycles, and timing is really important if you're doing this. Timing is super important. So maybe we can do something in CPU, like CPU.get next. Public void get, or it's not going to be a void, it's going to be int get next. And so what that's going to do is it's going to get the byte after the program counter. And then it probably should increment the program counter. So we're going to say int data is going to be equal to mem.read program counter, and then we're going to increment the program counter, so program counter plus plus, and then it's going to return that data. So that basically allows us to get the next. And so we also need to use opcode, so we could probably just do public void run. And we're just gonna say, and not really while, but like, let's do clock. Let's do one, like we can do the CPU cycle in the Game Boy. So, so clock, this will be get next. This let opcode equal this dot get next. And, or it's not let, it's int. I have to remember. And then somehow we're gonna say ops dot run opcode, and then that runs the opcode in the opcodes. And we also probably need a run, so public void run with a integer as its little thing here, and then that allows us to actually test this. So there we go. So that allows us to run the opcode. And so how are we going to do that? We could have a giant if we could have a giant switch statement, and we could just say if it's this, then run this. I mean, it could work. I mean, it's, yeah, sure, why not? So switch opcode case. What's going to be the case? 0x. I think the first one's 6. Is that what it is? 06. All right. So, and then that's in hexadecimal. So go over here. So if this is the case, then we are going to do load in and then we need to, I think I'm gonna have like where it's all like the same, and then we just have an argument load in character B, and then we could just have a char register. I'm gonna actually press tab there, and then break. And so this could be the general what's gonna happen. So, or have a bunch of case statements, and then it just has a bunch of arguments, and then we could probably have a bunch of if statements in here saying if register is equal to B, we can have it like saying int data equals CPU dot get next, and then if the register is equal to B, CPU dot get register BC dot set register 1 equal to data. And we can do that for the rest. I know we can do switch statements inside switch statements. And we probably should do that just for formality and being like, oh, it's all the same, looks all cool. I know this is not the way that anyone would do that, but this is how I'm thinking of doing it. Yeah. So if it's case B, then we're gonna do this, and then also just say break, and then we don't need that anymore. All right, so we should probably test this to see if it runs. So we can do that by setting the program counter to after public string test, and then we can make our own little test program here, and then mem.load to ROM test at 0x100. And so this will load it after this huge little bytes. So 8. Yeah, that'll work. So this test one is just gonna have load B with 255. And then that should work. And then I'm just going to go into our CPU and just say the program counter set to, where is it? Program counter set to 100. And then here's the moment of truth. Oh, hi. Oh, shoot. Someone had said something in the chat and I didn't see it. Okay, it was only 3 minutes old. Sorry about that. Hi, Mechanist. How's it going to you? I am doing pretty fine. I'm just making a Game Boy emulator over here. It's pretty cool. Hopefully it is pretty cool to you. Yeah. I just whatever. Just doing what I'm doing. Anyways, so let's actually test this. So emulator. I'm probably just gonna have like gameboy.run public void run. And this just runs everything, and then in here I don't really have to test any of this. I can just say emulator.run. There we go. So in here we can say CPU.clock, and then I'm just going to actually test system.out.print line, and then we can do CPU.register.bc.get register1, which is B. And then that should actually work out pretty good. I'm actually also going to get the program counter just to see if that has been incremented as well. So CPU.program.get program counter.get program counter. And there we go. So the program counter is, so we got register B, which is 1, and then the program counter is 257. Alright. Actually, I don't think we just need to do clock, because, or we should do clock, we just shouldn't put the program counter back, where's that? CPU, program counter, put at FF. So that also didn't work. I'm just going to test something as well. System.out.print test. Does it get to here? Let's see where it gets to. I know I could be doing some awesome debugging with the IDE, but I think this is just much better. So the CPU.clock console.log opcode system.out.println opcode. So the opcode is 80. What is 80 in hexadecimal? Hexadecimal to decimal converter. Swap. So 80 convert is 50. So it is at 50 on the register right here. So if I go to the Game Boy, it is at the wrong one. So I was at the right one. So I was doing the right thing. Hopefully what I was. So this should be at 0x100, and this should give me 0. I don't know why it's giving me some problems. So that's 0. That's weird. If it's 0, I have no idea how it works. Though. It looks like you're remaking a CPU for the Game Boy, I think. Yes, I am. I'm trying to do this one like process at a time. Because if I just go in and I try to create everything at the same time, it's going to be overwhelming, and then I don't want to do it because it's too overwhelming. So I'm just going to take this one step at a time, and I'm trying to do the CPU first, and then move on from there. Because without the CPU, you can't really have anything. So, right now I need to see why I am getting 0 opcode. It's weird. I really wish I can see the array, but I can't. I'm just going to test the run system.out.print line mem.read CPU.program counter. So this way I can actually see what is at the program counter. It is 0. What if I try doing it in the actual CPU before the program counter gets incremented? Oh, that's what it is 0. This is just strange, isn't it? It's like, so then, what if I do it the other way first? What if I increment the program counter and then read it? You can print out an array with a loop. I could do that. I mean, I know how to print out an array. It's just called arrays dot print, or not print, just arrays dot toString. I could do that. It's a really big array, and I'd rather have my computer and not blow it up. So, and of course the array I can control what is printed, but then I could probably just make like utils class. Let me just do that. Print or new class utils, and we can just in here we can have public static we could just it's going to be void print array, and we can have a few of those, like one that just has the array. Oh shoot, how would you like print print array, and it's assuming it's an int array, and if it's not, oh well. Array, and then this is just going to be for int I equals 0, I is less than array dot length I plus plus. It's just going to say and I could do system dot out dot print and then it's just going to have this little thing, a square bracket. I'd say for building such a complex community, you just need some decent debugging function to be able to see the information. Yeah, that's what I was thinking after a little bit, but I'm doing it now, so don't worry. So I need array of I plus a little comma just to show, and add, and then at the end we should print out the end bracket. And this is actually going to be looking really strange because then at the end it's going to have a comma and a space and then an n. So if I is equal to array dot length -1, that means it's on the last one. Print this, else print the normal one. So else print that. If it's not, then just print the array. Alright, so that's just some simple debugging. And what I can actually do is I can do public static void print array int array and then int start int end, and then I can have everything based off this one function. And then once, if you call a different function, just these parameters are already set in that, and it makes it so much more easier. So if it's the end, it is the end. And the same for this one, we can have public static void print array. I feel like this is just very simple stuff, and then this only has the start int start. And then once this, and then when it is called, you just call this dot print array, or utils, because it's static. Utils dot print array, array starts 0, and then array dot length. And then that just makes it so I don't have to copy and paste code 3 times and make it all jumbled mess. And then this one is just at the start. Alright, so now that I actually have all this, I can actually print good stuff. So just to prove this, or just not to prove it, to test this, I want to print out the first 256 bytes. So no more checking if the thing works. I am going to check if the memory is working correctly. So utils.printarray, what array? So memory dot. Do I have get memory dot? I don't actually have a way to get the entire array. That is kind of a stupid decision. Alright, so I'll just say public void get memory, and then just return int array. Int array. And so return this, just return memory. Alright, so that makes that a bit simple. So now I can say memory mem.get memory. The start is 0, and then the end is 0xff. Actually, just for formality, I'm just going to do that. And there we go. So we have just a simple way of printing the array. And here we are. So that prints it good. Oh, well, that's not right. It does the end weird, like I said it would. Maybe it's just if I is equal to the length. Nope. No. Should I have like a print array as hex? Yeah. So basically the same thing, except it's print array as hex. Print array as hex, and just have all this the same. However, instead of just naming the array, it's just going to do integer dot to hex string. And then the same here. And so that just allows me to see if that's actually working, because these are just normal numbers, and so I can't really see that. Let me find where, see in a Gameboy? It's in Gameboy, so print array as hex, and that allows me just to see it as a hex array. So yeah, 31 FE, FF, AF, 21F, and so yeah, 1, 0, 1, E0, and then I needed, just do that. Oh, I know the problem. It's because I used a different end, and I used that. There's just a lot of complications with this, and I did it differently. So, yeah. So instead of using array length, I'm supposed to be using end, probably -1, and then the same as right here. And since I know it's -1 because length is always greater. And yeah, there we go. So now, if I go into the boot ROM, we should see E0 and F0 as the last ones. And there we go. So that is how we're going to be printing arrays for debugging. And thank you for that, Lawrence W. That is actually going to be helping me in the future. So to actually test this now, we need to see why this is not printing what I want. So I'm just going to print 10 addresses, and it's just all 0. That is not working. I know that's not working. So what is going on here? So I don't need utils right now. Opcodes I don't need. I need memory and seeing why this won't load to ROM correctly. Is it because it's 1? I don't know if it's because it's 1. Let me utils dot print array. Oh, that's also an int array. Can I do object array? I can't do object array, right? I can't. I'm just going to test it with the first one. I don't want to utils print array object. Dang it, I have to change them all. Object. Oh, that's not right. I have to just fixing all these things, fixing all these things. Boom, fix them all, fix them all. Bytes. So yeah, that works out pretty well. And then this is the second one. So yeah, the second one should work. Let me try this. Oh, and then we should at the end print a line, because, or at least put a line break in there. Back end. That looks right. Oop. Yeah, oh, well. Yeah, that's probably not good. You just kind of printed a very long array twice, or how many ever times I did it, and yeah, it does work once. but it doesn't, it doesn't want to do it correctly. And I'm actually going to change this object array to this int array, all this because I know it works. And just do that. It's just going. It's probably gonna make an error if I do anything wrong with that, but oh well. Okay, so yeah. So I don't know why this is not working. Why? And I'm just going to press play to clear the console. Oh wait, an error exists. Yeah, that's what I thought. So maybe with this one I can just keep those as ints and then print array as object. I have to do so many more things with that. So int array. I could just copy it and then paste it to be like int string, and that would be it because there's no floats or any of that in the array. So yeah, I could do that. Oh, let me undo all this. I gotta fix that once again. Print array, but as a string this time, and then fix all those with that. And then print array as hex has got to be fixed here and here. All right, so now I can actually print correct things now. So yeah, okay, now it's cleared. Okay, so so I times 2 is equal to integer.parseInt, and then it takes the substring. And so I'm actually going to test what that is. So system.out.print line memory of I times 2. Yeah, so that's correct. Well, let me see what I is. So it should count up. Wait, 127. Oh, that's right, because it works for both. And so I is 256. Wait. That could be a problem. Oh yeah, that definitely could be a problem. Wait, no, it isn't though. Because in the end, bytes length minus 1. Bytes length minus 1. You could be right. Wait, no, but it doesn't matter because we're using the less than. If it shouldn't matter there. So let me print a bigger section of memory. 0x or just 0x 0x00, and let's go to 0x200. Maybe it's in the next couple bytes. Alright, so we have all the usual stuff, and then we just have a string of zeros. And that's it. And look, and then the test ROM, which is 06FF, which I can just, hold on, control find short, so 6-FF, find, oh, it is found. Oh, but that's 26FF. It's not, yeah, it's not found. And 26FF is right there. And 06FF is never found. Alright, so start. So the start. What is start? System.out.print line is start. And that is actually going to be converted to decimal, so I know. So 0 and 256, which is right. That should be right. And so start and then start plus 1. What I think is happening is that it's being written at 512, so because 256, you know that all that. So start divided by 2. Start divided by 2 plus bytes.length. Java exception has occurred. Index -128 is out of bounds for length of 1. Well, that's not what I wanted. Well, why was that? What if I do just start divided by equals 2? Yeah, okay, that works. Alright, so now if I go to the end of it where it's just a bunch of zeros, there it is. Ah, okay, fix the issue. So now we have everything's working here, and now it's the same problem is fixed. So that way, if it starts at 0, I mean, that doesn't really do anything, but then if it starts like at 2, then it should start at 1, and then 1 times 2, and then do all that correctly. So there we go. Now we have that. We have it working. It is fixed. There's one thing that, okay, utils, because I had to test a bunch of things. So there we go. So now if I do 0x100 and then 0x100A, it should see 6FF and then a couple bytes later. And that's for my test program. And that is correct. So that means if I finally do this stuff, I should get 255 as the B register, which is correct, and the program counter is at 257, which is after the fact of. So it works. It's working, and it's great. Finally, how long has it been? It's been an hour. It's been an hour, and I've done one instruction. We're going great. So that way, so now I know that opcodes are working. Let's add some more opcodes. So, let me go here in the CPU manual. Let me go full screen on this one. Alright, so there is 6 of these types of instructions that go to all the parameters, and this just is so. And we can actually do something like this. So all the 8-bit loads, so this basically just loads a register into it. So yeah. And now we need to do the same for the rest. Boom, 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 and boom. Let me go here. So 0, 6, 0E, and then all the way. So E, 1, 1, 2, 2, E, E. And this is the same for all these. So we have C, D, E, H, and L. B, C, D, E. Okay, so we need C, D, E, H, L. And then we could just add this as well to our case statement. So boom, 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 and boom. Alright, so let's go all the way down here. Let's do L, H, E, D, and C. And just to change all these, 2, 2, 2, DE, DE, HL, HL. And that is correct. So now we have B, C, D, E, and HL, and that's just our first 6 of them. And I think that's pretty good progress. I mean, going from an hour to going about an hour just to do one command, and now we just did 6 commands in a matter of like a minute. So this one's probably going to be a bit harder. Holy crap. As you can see, because it's all these different types of register loading things. There's a bunch of load functions. So yeah. So let's go in here and just say it's a new one. It's just public void load r because it means 2 registers. So char register 1, char register 2, and then we have a switch statement here. So if the first register is A through, what is it? A, B, C, D, E, H, L, and then the address of HL. So these are going to be strings, because these sometimes have to have multiple strings. So we can have A, we can have B, we can have C, we can have D, we can have E, and we can have H. And then we also have L, and then the address in HL. So HL, and then the address of HL. And these have to be string quotations. And oh yeah, these have to also be string. And so do all that. I'll fix all this. Oop. There we go. So this basically allows us to, and then we can put a couple of switch statements in. Actually, I have an idea. So instead of doing all these switch statements, we can have 2 functions. We can have one switch statement basically. Public void get register, and it's going to take in a string of a register. Oh, and it should return an integer. And this is where like one only switch statement is. So these are all the registers that actually matter. So we should, oh well, I got to take the entire register. Now let's do that. Tab this over. This takes in a register. This should return CPU.getRegister psw.getRegister A. And then semicolon. Burp. Excuse me. And then we need to return all these registers as well. Actually, I'm going to do one register. So get register BC and then get register 1. And then the same for all these. And so instead of having all these switch case things in the instructions, and then that's just going to be a ton of switch stuff, we're actually just going to say get register of that register is equal to whatever. And we also should have a set register, and it's kind of obvious what that one does. This one's a bit different because instead of getting the registers, we actually have to get the address. But I'll do that once I get there. So every second one has to be 2, so 2, 2, and 2. And then all of these over here have to be different. So HL, HL, DE, DE, and is the status register? I would say the status register is also part of this, so wait. Okay, I guess we can break. I don't think we need breaks here because it's returning something. And then I think we should also have and then return. We can actually say return -1 here because I don't think any of these numbers actually go negative, which is pretty cool. And so get status. What's the actual get status flags? And this one's just going to be called F because the F is the status register. And then I actually have to do HL. So return CPU.mem.get memory. Oh, the CPU doesn't have a get memory. I can do this. Just copy that. Attach memory. Get memory. Get mem. And then opcodes, I can just do CPU.get memory.read. Wait. Oh wait, what? Return. Oh, this has got to return memory. And then this dot get memory dot read, and then CPU dot get register HL dot get register, like the entire register. And that should be our get register function done. We should also have a set register because we need to set a bunch of registers. So set register. And then we just have int data. And so basically, instead of saying set or get, we need to say set. I also put the data in, but I'll put that in once I actually set the register. And then set that, we need to not actually do return, we need to void. And so this doesn't need to actually return anything. And say data instead and actually put that in there. and then this one is going to be write whatever's in the register. Ooh. Oh yeah, and then I have to say data. Alright, so just a bit of helper functions to get us started. And this should actually save us on a lot. We're going to say this dot set register, and then data. And we do a string. And we gotta do the same thing here where we set the register. And there we go. So now, so instead of doing this, we could just say this dot set register, and data. And we can also do the same for this one. So this dot set register 1 to this dot get register. So this dot get register 2. And that is actually going to make our lives, well, my life, so much easier. So this loads the next data, so load next, and then it gives us that. And then this one is just going to set the register to the next register. And so now we need to actually implement all this into here. So there's a lot. So A, B, C, D. So A to A, which kind of doesn't make sense, but if you want a complete thing, we just probably should add it. A to A, A to B, A to C, A to D, A to E, A to H, A to L, and then A to that address. And that basically just loads whatever's in A into that. And we don't have to do that because why would you have B to A on there? Because it kind of doesn't make sense. Or it's later on. Load A to N. Alright. Oh yeah, here it is. Alright. So apparently I was wrong, and so now we are actually going to be implementing all these instructions. So load register to register is going to be here, and so we need case. What's the case? Yeah. 75, 78, 79, 78. So 0x7f is going to be this dot load register to register, and it loads register A to register A for some reason. I feel that's kind of useless, but what do I know? And so now we basically need to do that for the rest. So we got B, C, D, E, H, L, memory. And of course, B, C, D, E, H, L, memory. And we should also, and we probably should keep adding like get register and get all that, and then so, alright, so 7F, 7, 8, 7, 9, so 8, so it's 8 through E, so 7, 8, 7, 9, 7A, 7B, 7C, 7D, and 7E. And so that is all added, and we now need to do the same thing, but for B and all the rest. So B, 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 B. And then 40, is it 40 through 46? 40 through 46. So 40, 41, 42, 43, 44, 45, 46. And so that's actually, this is going to be a lot of these. There's going to be a lot of case statements right here, but what are you going to do? And yeah. I'm probably just going to have comments at the end of this, like after I'm actually done with it, actually describe what each of these do. But right now I don't need to. And then, so instead of saying B, we need to say C. And now it's going to be 48, 49, A, B, C, D, and E. And we need to do the same for D, and I'm assuming it takes on the next one, so like 5. Yeah, 5. So 5. Probably just copy, instead of this one, we copy this one. And we just say 5, 5, 5, 5, 5, 5. And say D, 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 and D. So there should be 7. And there's not 7 because I accidentally took out this one. D, and then 5, 6. And we need to do the same for that. And we can say 5, 5, 5, 5, 5, and 5. And then C, 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 all that. And we gotta say, so that E, 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 E. And I'm assuming this goes for 6 and for 7 as well. So we can actually go from this to here. And we can just say 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, and 6. This is going to be pretty boring because there's so many freaking load instructions. But they have to be done. Like, I could have actually done what I was going to do, have switch damage for all of these, and that would have just been a disaster, and then I would have to do what I'm doing now as well. So I'm glad I simplified things a whole bunch. And yeah, that is a lot of instructions. Look at all these instructions. So, wait. And yeah, these are just all load instructions. Look at it. Look at all these load instructions. Yeah, and then we also have, and I was looking at this, we also have to, like, if it's CB, we have to use a separate opcode table, which is not that hard because opcodes, we could just add function saying, alright, it's just like carry on, but on another one. Yeah. What is that? I apologize. Uh, so that's probably not going to be cool. So uh, hey, live stream fails. If that is ever caught, I highly doubt it's ever caught. Because I'm not a big channel, and if I was, I mean, if I'm a big channel, then it'd probably be like, oh my gosh, someone is in there. Yeah, but it's fine. Anyways, let's continue on. Let's do all of this now, and so now we're at the point to where we have to do a bunch of HLs. So I'm just going to copy this. Oh, I forgot to. This is supposed to be L. Yeah. All right. So now instead of saying H, we say HLs all around, and just copy all of that. Does it also do HL to? No, it doesn't do HL to HL. Does HL to what is called N, and so N is the next byte. But yeah, we can't really the immediate value. So we should also have to have B, C, D, E, H, L. That's going to be in 16-bit loads. That's not going to be right now. So we need to say 70. It's 70 to 75, and then the last one is 36. So 70, 71, 72, 73, 74, 75, and 36. So HL is being loaded with N, and the problem is that we do not have N, and so we should add that. So N is the next one. N is right here, and so if we say, okay, return CPU.getMemory.read, it's probably just going to return CPU.getNextByte. Return CPU.getNext. That is also going to increment the program counter, and I don't know if that's going to affect it in any way. I don't think it will affect it. So if we set the immediate value, I don't think we're ever going to be setting the next immediate value, because if we're setting the next immediate value, why would we be doing that? So Thank you, Lawrence W. Crap. That's a fail right there. Thank you. I thought I was talking to someone and I wasn't. So anyways, what I was saying is that we need to be working on Hi Hero AX or AX or whatever you like to be called. So I was just talking about how we need to do the registers of BC and DE the same way we did with HL. So except BC and DE. And then I was talking about in Little Indian, and I was talking about how to pronounce in. That's why I pulled up the pronunciation, and then I pulled out what it actually meant. So I think that's it. And then now we're where we are right now with after the fail. So now we need to talk about, now we need to do this, and this one's going to be more than just one line. I mean, I can make it one line. I probably won't because that's. So I'd probably just say let or int address is equal to, or int the significant byte is equal to CPU dot get next, int most significant byte is equal to CPU dot get next, and so we need to combine them together, and that's going to be the address, and then the CPU needs to read that. So same right here. So CPU dot read. So the most significant bit needs to be shifted to the right 8 because remember working with bytes, and a byte is an 8-bit number. So, and then we need to OR that, which basically means combine it with the least significant bit, and we don't need to shift anything with the least significant bit. So I could make a helper function, and I probably will actually, to convert two 8-bit numbers to a 16-bit number. So public static void convert 8 to 16, and we're going to have int least significant bit and int most significant bit, and basically I'm just going to return. I'm basically doing what I did for the opcodes except as a function, so I can make it more better. So return most significant bit, and then probably shouldn't have void. I probably should have it. So there we go. And so now what I can do is I can do utils dot convert 8 to 6, least significant, most significant, and that makes sense. So and return this. Return, and that is the same way I'm going to be doing inin, except I can't really be doing that. I don't know if I'm going to make a function for this one because I have to convert 16-bit number into two 8-bit numbers. So set register inin. So actually, I know what it's not that I actually I don't convert 2 bits. I just have to say CPU or CPU.write the 16-bit number and then with the data. So I thought that would be more complicated than it actually was. So now that we have the inin address, we can actually add that. I will be going into cycles probably, just adding that a bit later on, because right now I'm just trying to see if these instructions will work. So this is going to be case 0xFA. This dot load register, which loads the A register into the address of the next 2 bytes in the break. So that is a pretty simple one to do. I like how I'm doing it to where I just have different function calls. So, and then this is the one that is different. It is actually so we've already done AA, but we haven't done BA, CA, and DA, as you see up here. So we skipped that, which I think is pretty stupid, but I mean, you do what you do. And it's because why did we skip that? Like, it's super easy. All we have to do is just do that, change this to B, and change this to, what is this going to be? It's going to be 47. So 47, and then this just loads register. Yeah, just loads register A into B, which I don't know why that wasn't in, like, the documentation is really strange with that. Like, so that's actually going to be F, and then we got to do the same thing for this one. G 57, E 5F, and then H 67, and then L 7F, or 6F, not 7F. And then is that the same as well as, and just to prove this, or just to test this, 6F should go into this L. You should have added a comment saying which page of the manual each group of instructions is from. You have such great ideas. So what I think I'm going to be doing is, after I get all these instructions done, I'm going to be commenting, not on stream. On stream, I'll probably do that on my own time, but like on, what I'm going to do is like say comment load H to C, and then like say load register C to H. However, I'm not going to be doing that on stream because I actually want to have progress on stream, and then something like commenting it makes no progress, but it does help, so if you know what I mean. I can also have 6F, and then have that to register. And so I can also have a program that does that. So you know, so 6F load H to Z, loads register C to register H. Understandable. So, and then I can also have the page number, like page, what is this, page 67? It's the one it's the bulk of these. It's page 66, so I can do that. And so that basically is so I can actually make progress on stream, and then that's just so you guys can see the cool stuff. Anyways, let's make some more progress. Okay, where am I? I'm here. Alright, so no, I'm not here, I'm here. And I do have to have these other 4. So HA, and then at the end we need to say, we basically need to flip these and say BC and DE and NN. And then that's just going to be in registers A, or A is going to be loaded into that. And then that is 02, 12, 77, and EA. 02, 12. Oh, I forgot HL. 77. Wait. I didn't forget that. It's just that. Wait. case it's probably because I did this, or I'm going to do this. Boom, HL, and then it's actually 77, and then 0202, and then this one is EA for EA Sports. Oh, I thought that was an error. I was like, what? Why is there an error? But there wasn't. Oh, it's down here. So yeah, and so now we need to do some this. So this is some special loading. This is actually called zero page loading on the 6502, which I'm very knowledgeable of. And this is to where you have, well, it ain't really a zero page because this is actually the last page. I'm talking about pages like you guys know. So what a page is basically the most significant bit. So like page 1 is where the most significant bit is 00, and the last page is when the most significant bit or byte is the most it can go, FF. And so this is how we use last page, like addressing or whatever in here. So put the value of address FF plus whatever's in register Z or C.Z C into A, and it's kind of it gives us a little how it is. So yeah, so it is basically this, but like, see, so I I'm probably just gonna do public public void load and then last page, and then this is just gonna load register, and then string offset register, because I bet there's gonna be more zero page loading like this. So load A, put the value of HL and the value of address HL in there, and load HL. Okay, so that is a separate one as well. Register 2. I just had like a blank moment there. So this dot set register. Register is a last page, and then I actually think that's, is there any others? I'm actually gonna search that up. Control F, in parentheses, FF00 plus C. And there's only 4 occasions of this. It's when it's doing that. And what's the first occasion? Or when's the first occasion? That's the first occasion. Okay, so yeah, this is the only occasion to where last page is ever done. So I am going to be just saying load A to last page, and this says set register A to CPU dot get register BC dot get register 2, because it's register 2 C, plus actually I should do it the other way just to make more sense. to where 0x ff0 plus this. And then that's the address, and then we have to actually read whatever the address is. So this dot or CPU dot get or CPU dot get memory dot read, and this is the address. So yeah, I already explained how it works. So now I'm going to have the other one, which is load last page to A. Last page to A. And it's basically reverses it. So it sets. I'm just going to say CPU dot write whatever it is, and then this dot get registered. And I could do the CPU dot get register, right? But I'm already doing this here, so I mean it's already there. So I know that could save like on function calls, but it's just for uniformality. That's not a word. Uniformality. So now I've done zero paging. We can do this one. Oh, these are all the same. It just confused me. Alright, so this is load and decrement. So this is also going to get its own. So public void load decrement. I think it's fine. It's only a function and it's not going to be called much. Yeah, I don't think it's going to ruin performance. I think what's going to ruin performance is that it's Java, and Java is not the fastest language out there. But it's faster than, say, JavaScript or Python. It's like in the middle of the speed, and it's good for like for old consoles, like old consoles. Like, well, Game Boy's not really old, but it's good for the Game Boy basically. If I'm going to be doing a really like sort of new console, like anything that's 3D, I'm not going to be using Java at all. I'm probably going to be using C++ or C, or I'm going to be using something close to that. Alright, back. I said no to food basically, but yes, Java is flawless. Oh yes, it is very good. Rolled my eyes there. Well, I also forgot to do the opcodes for these two instructions. So this is F2 and F3, or E2. So case of 0x F2, this dot load ALP, and then if it's E2, we load LPA. It's basically the other way. So LPA and E2. Is that right? So it loads whatever the value is of there into A, and then it loads the value of A into there. So I think that is pretty good. And then for load and decrement, I haven't done that yet, so I will do that. So load and decrement, it loads, I think, the value of HL into A and then decrements HL. So, alright, so put value of address HL into A. So, that's easy. That's just load this dot load register to register. It loads A into, or loads the address of HL into A. And then after we load it, we need to say cpu.get register HL dot set register, and then it gets the register -1. And that is a long process of just saying HL -, and dot get register -1. And there we go. So now we can actually add that. What is the opcode? It is 3A, so case 0x3A. This load decrement. And we also need a bunch of breaks right there. So there's that one. We also have this one's a different apparently. Put A into memory address HL and then oh, this is okay. So like say you want 10 address spaces to be all 10. So you load 10 into A, so you could say load A 10 or load A and then the hexadecimal A because A is 10. And then you can set your HL or load H as with the least significant bit, and then load L with the most significant bit, and then just call load decrement 10 times, and you should have 10 in the 10 addresses before. So that is basically the same as this. So load decrement, and this is AHL, and then load decrement HLA. I have to change the name of this now, so boom. And so we load HL, or we load A into HL, and then we decrement HL the same way, except, and then now we say 32, is it 32, is it 32, or is it just 32? Okay, 32, and then HLA. Alright, so now that we got that working, we can do the next one, which is it load increment? It's load increment. I know what that does. So load, is it LDI? It's LDI. So LDI 8 LDI, and the only difference is it adds instead of subtracts. So a lot of these are the same, except they're different because of how they are done. So it's 2A and probably 2. So load I and load I, or load increment. And 22, yep. Alright. So now we have some more zero page. We do have more zero paging stuff. Hold on. I thought we got rid of it. So that's zero page, that's zero page, that's okay, so that's last page, last page, last page, last page, and then that's that. All right, so hopefully this is the last one. I thought I got away with it, but I didn't. So this is so we need to basically and then we can have, I have an idea, so we could just say int, or not int, string offset register. And that's probably what we're supposed to be doing. And so it is offsetted by the offset register. So if the offset register is whether or not it's C or N, it's well I'm talking about. So now I need string offset register, and then this is just for C, and this is for C, and now I need to do the same thing but for N. Is it okay? So it's E0. So put A into the memory address. So E0 and then F0. And then this just loads into it. And N is right here. And so that also saves a function call right there. All right. So now we are on to 16-bit loads. Put the value of NN into N. So if you remember how we got the NN, this is how we load B, C, D, E, and H, C. This is basically how we do 16 bits. And so this is the same of LDN right there. So if we set this so we also need to actually change that, because these are all addresses and these are not all the registers, these are just addresses. So now what we need to do is we need to say case BC, and this returns CPU.get register BC.get register, and this is just how we get the other ones, and then we can do set register HL, and this just changes DE HL. So pretty simple. Now we need to do the same thing for the other one, except it's called set. So I'm just going to copy this one, dot set register data, and it's the same for all of these. And it needs to be the same for this one. Yeah. Alright, so, and then the data doesn't matter because it's just assuming that it can actually fit that data. So set register data, set register data, set register data. So easy peasy. Also, I just finished my drink. Nice, landed. So if we want to get NN, because it's the immediate value, as you can see here, we need to do the same as we did for the address of NN, but we don't get what's in the address. We just get NN. So NN, least significant bit, most significant bit. All right, let me just do int least significant bit equals 0, most significant bit equals 0. And then now we just get rid of all these int calls. It should fix it. There we go. Okay, so now we just need to return the convert 8 to 16-bit, least significant to most significant. So now we can actually call this. So we can do, what does this call it? Is it 0, 1 to 3, 1, and then we also need the stack pointer. Stack pointer. So stack pointer is also pretty important, and so we need to say get stack register stack pointer and set stack pointer. Case stack pointer, and just return CPU.get stack pointer. This one's a bit more simpler than the registers. It's because the CPU just has that. And then this return CPU. No. We just say CPU dot CPU dot set stack pointer data. I also forgot that we needed breaks here. Oh, that's gonna suck, cause that's gonna suck real hard, cause we need breaks or it's gonna have a error there. So there. It wasn't too bad, but I'm off for now. Good luck. Thank you, Lawrence W. See you later. Hopefully you can see the rest of my stream on my channel. So if you want to watch that, you can. It'll be up probably a couple hours after the stream is done. So yeah. Anyways, let's continue on doing our emulator business. Woohoo! So once again, I don't think I need to be setting the immediate next 16-bit value because that doesn't make sense. So I won't be putting that at set, but I will be doing these instructions. So loading register to register is actually going to work here because I put these are all registers now. So load register to register. Register 1 is going to be BC, and then register 2 is going to be NN. And so since I'm not really limiting 16-bit and 8-bit numbers, they're all ints to me, it's going to work out. I think it's going to work out pretty good. So, oh yeah, we also need breaks here. So break, and we also need these two cases here. So we need HL and then the stack pointer. And these need to be 2 and 3 respectively. So we've already got a whole bunch of opcodes. I don't know how many we have, but it's a lot. And these are just all loading stuff. So the math stuff takes up the rest of it. Yeah, look. Boom. Look. Now we have push. Push is just going to be another thing. Alright, so now, so we have the 16-bit loads. We load 16-bit value into BC and D and all that. So we did that, and now we need to load the stack pointer, or we need to load HL into the stack pointer. And that is F9, and that's pretty simple. So case 0x F9. This dot load register to register. It'll load stack pointer with HL. HL, there we go. Working out pretty good. So go back to the CPU. It's not really hard. So put SP plus in effective address into HL. Oh, flags affected. So, So there's actual flags here, so now we need to actually work with flags. See, flags aren't really affected loading, because why would it be affected for loading? There's no adding or subtracting or any operation done to it, it's just you're setting that value. So I wouldn't say there's much of a problem. So put the stack pointer plus n, which is the next byte, and it's signed. As you can see, it is signed. So we have to actually take care of the negative. So if the first byte, or if it's the 7th bit, or the first bit from all the way to the left, if the most significant bit is 1, that means it's negative, and that means we have to treat it as such. So then, and put the stack pointer plus n effective address into HL. So this one's going to be a bit of a complicated one, and it's the only one of its kind, so I'm going to put it as its own function. Public void, and then we need to do load HL SPN. Just load SPN. So now that we have this, we need to do the put SPN, and it's a signed byte, so we should probably figure out what this byte is. So we need to say int signed byte, so s byte is equal to cpu.getNext. And then with this, we can take that, and I could just do this. Nah, it's fine. So cpu.getNext, and we need to say if s byte and what is binary converter? Binary to hex, please. Binary to hex. So 10000000. So this is 8. This is 8. This is 7 right here, and this is 1. And this is basically if the first one convert. So if s byte and 0x80, that means if the first one is equal to, and then is equal to it, that means we have to make it a negative number. So that means we just basically subtract 255 from it. Wait, what? Put bit operations in parentheses. Alright, that's just an easy fix. Alright, so if it is negative, which is basically what it's saying, we need to actually make the byte negative. So s byte minus 255 minus equals 255. So that basically makes it negative if it's supposed to be. So say this turns into, and then maybe I can hex to binary. No, I need decimal, or binary to decimal. Yeah, there we go. So if 1 2 3 1 2 3 4. So if it is greater than 128, then we subtract 255. So if it's 129, 129 minus 255 is turned to 126. If it's 128, that means it turns into negative 127. I actually think, is it signed byte range? So signed byte range, it goes from it is not. It is actually a negative 128 to 127. So subtract 256. So that should work. So that means if it's 128, that means that's the first negative number basically. Then it is 127 and so on. So that is how you convert a byte into a signed byte, is you basically subtract 256 from it. And if it goes over 256, it's an overflow, and so yeah. And so let's go back to the CPU manual. So the 0 flag has got reset. The what is that? Subtract flag in negative? I don't know. So that flag has been reset. So we need to do cpu.get program state word register. So set flag, and that is psw register dot zero flag, and that is set to off, so false. So false. And then we need to do the others for the other flags. So subtract flag is also reset. It means it is turned off. The half carry and carry is set accordingly. So I don't know, but I do have to go to the bathroom, so I will be right back. Well, I am back. So, hello. So I'm just here again. I went to the bathroom. That's it. So, anyways, so we have load HL, and then this probably should be called load HL then. So load HL. I did notice that. So we have to set the half carry flag. Half carry flag, and we also need to set the carry flag according to stuff. So we don't reset it. We actually have to set it according to stuff. So I think what we need to set it to effective address. What does effective address mean? That is effective. So effective address. What is effective? Effective is only used there. No, it isn't. It's just oh, it's weird. Well, there's only one. I think effective address means that it can actually, be caught, because maybe the stack pointer is over that, and then it overloops. And then so we need int address, and that's going to be equal to cbo.get stack pointer plus s byte, which is signed byte. So cbo.get stack pointer plus s byte, and then we need to set that, and we need to go in there. So if address is greater than FFF, or address is less than 0000, that means that a carry has been set. So we need to set that. Actually, we could just do it like this. We don't even need an if statement. We just set it like that. And then we need the half carry flag to be the same. So boom, except it's a bit different. Half carry flag is when the bits from the lower significant bit overflow into the bits of the most significant bit, or the higher significant bit. So we need to somehow test that. So, I don't know how to really test that. So, okay, so if an S byte is just okay, I think I know how to do this. I'm gonna do it as an if statement first, and then do that. So if address and whatever and 0xff, and we have to do that in parentheses. So if address and 0xff plus s byte is greater than 0xff. Alright, so yeah, I don't know if that will work or not. I will try. So my logic is, just put that in there. my logic is that if the address and the least significant bit, that means it's like and then plus S bit is greater than the FF, that means it's gotten to another byte. It's gotten to the third byte. That means that it has carried over, and it requires the half carry flag to be enabled. So hopefully that works out pretty good. So let's just see how that works out. And also, we also need to limit the address. So address, and then same as the S byte. If it is greater than it, we just subtract it. So if address is greater than 0x FFF, address minus equals 0x FFF, and that just loops it all the way back around to 0. And if it's less than 0, 0, 0, 0, you add that. And so that should basically just loop it around if the address is greater than what it should be. And I was also looking at this, and I also saw that this is actually like just some code, and we can just have string register 1, string register 2, and we can just put that in here, and then when we call the function we can actually call which one it is. And so now we can just say load that, and we don't even need two functions anymore. And similarly, if I can speak, we just say plus when it is load increment. So yeah, and so now this is broken because, and I'm glad I kept that because I would not have remembered what it would have been. And it's the other way now, so in parentheses HL, and it uses register A. And boom, now we need to load, and then this loads it, this adds it, or increments it, not really adds. There we go. So now, now we need to do LDHL when F8 is reached. So case 0x F8, we do just LDHL, boom, and this just loads and it does all that it's supposed to do. So that was actually the most complicated thing that we've done so far. So there we go. So now we need to put the stack pointer at address and in, and man, we go from something this complicated to something simple. It is basically case, and I think it's 08. That one? Yeah. So this needs to load, so this dot LD register to register. It loads the first, it loads what the stack pointer to and in. So this loads stack pointer with address and in. So that should work out pretty good. So load, put stack pointer at address in, and then that is the correct one. Alright, so now we're getting on to separate ones from load. So we have push and pop. So I think we're done with loading. Dang, that's a lot of loading instructions. I wonder how many there is. So it goes from, it goes from 14 all the way to 105. So 105 minus 14. There is 91 load instructions. So there's many ways to load something, so you have many, like, you're not just going to be stuck having to do more than one opcode basically. So yeah, I guess we can add the next one, which is push and pull. And there's multiple pushes, or push and pop, not push and pull. So push and pop. So we've done all these functions. Now we need public void push and public void pop. And so there we go. And what do we need to... So this pushes the register pair in onto stack, and it decrements twice. Alright. So it pushes... Okay. So it pushes whatever, so we need the register that it pushes, so string register. We also need... And is the pop the same thing? Pops 2 off... Okay, yeah, it does the same thing. So string register, and then in here we need to say this dot get register, and then it needs to push that onto it, which basically is putting it to where the stack pointer is, and then we need to decrement it. So we need to do cpu.memory or get memory dot write at address, which is cpu.get stack pointer, this dot get register. So there we go. And then we also need to cpu.set stack pointer, cpu.get stack pointer -2, because we need to do it twice because it's a 16-bit and all the data is... Oh wait, that is also true. It is 16-bit and they can only do 8-bit, so we actually have to separate these two into multiple ones. So we need to do this dot get register, register dot get. We can just do CPU. We have to do this dot register, this dot get register. And for this one is for the first one, so we have to do I know what we could do, but that just makes it more work. And it doesn't make sense if I look at this later, so I'm just going to do what I think I have to do. So this gets the first one, and then we have to do the second one, which is stack pointer -1. And then we need to do, this dot get registered and 0xf. And so this just gets the last, and this gets the most. So there we go. I think that will work out, and it will work for all registers. And now we need to do the same, but for pop, which is basically setting the register equal to that one. So we have to set the stack pointer up to, and then we need to read. So read read. And actually we need to say this dot set register. Register is equal to the register and then the data, which is two reads actually. It's not a bunch of reads. So CPU.getMemory.read and then whatever the stack pointer is. So I'm actually going to copy that. And boom. Alright, so this gets the stack pointer. And then I think we need to shift that to the right. 1:30 a.m. Doesn't matter. I need to watch AP stream right now. Welcome back, E-Trade. Yeah, you are at a different time period. I remember that. You said that you had to go to bed because, what, it was like 3 o'clock. It wasn't 3 o'clock. It was 12. It was close to time. It was close to sleep, basically. So, what up? I mean, I'm not gonna say that you need to. I'm not gonna say that you need to go to sleep. But it is 1:30. I mean, if you want to watch my stream though, it'll be fine. It's fine. It's fine. All right. So. Yeah. So, well, I have to do this. So this dot set register, and then CPU get memory dot read. So the stack pointer, and this actually pops it off. So this sets it to 0. So push. Oh, well, I'm at pop. So pop 2 byte stack off it, and then so it writes it there, and it writes it there, and then it goes down, and then it goes up, and then we just need to basically set this. So CPU.getMemory.write, and then that's all I need. I could just put this right here. CPU.getMemory.read, and then -1, and then that is shifted to the wait, I don't need to read that. I need that. Still the holidays till the 11th. Dang. You get like, what do you mean still the holidays? I'm trying to see what like holidays. The only holiday I know of is Labor Day, and that is one day, and that is tomorrow. And we just get out of school, and it's just one day. It's not. So unless you're just not in school, which would be pretty cool as well. That project looks interesting. It is very interesting. We have basically all the load instructions in, and now we're doing some pushing and popping, and then we are actually getting to the math, which is the fun part because we have to worry about overflows and negative stuff and all that. So, yay. So CPU.getMemory.read, 26th July till 11th September. So, oh wait, that is your summer months. Oh yeah, you guys are still. You have like summer months. Wait, so I'm trying to think. You're in Australia, I think, because that's like summer months is fall month or winter months for us. I don't know. It's just that you're probably still in summer vacation. I say that with quotations because it's probably not summer where you are, but I'm an American, so I think of it as a summer vacation. You're at school break, basically. So, dang. Anyways, so now we need to get the stack pointer at, well, the actual stack pointer itself. So, yeah, however you call it, yeah. I just say school break, because I would say school break. No, Germany. Well, I was wrong. Well, you're just not in the United States, is what I'm going to say. Well, Australia is a different person. That's probably a mod on my Discord. I think so, because he had an Australian country with the Australian flag as it. So, well, So Germany probably has a different schedule than us. They probably have better schooling, or they have a better school schedule, not better schooling. I don't know about that. So yeah. So we need to set the stack pointer up to, and then we need to read. So we add it, and then we need. Wait. So is the most significant bit. I don't know whether or not it's the most significant bit. So we get stack pointer -1, and then that is and with 0xff. Frick. Parentheses are wrong. And so hopefully this is right. Excuse me. So now we actually have to add that into our huge switch statement. So what are these instructions called? So push is FCDE, and oh, we don't even have register AF. Oh, so we have to use get register, and we actually have to get it. So case AF dot get it's not register AF, it's PS register. I need some ideas. I don't know what to code. Well, I would say make a simple application for like, I don't know. If you want to make some, how do you get your ideas? Well, I just feel like, because I don't know how I get my ideas, but like sometimes like, yeah, I want to do that, but yeah, I don't want to do that, and it's super hard, and I don't know what to do. Like sometimes I get great ideas, and sometimes they're just ideas that I don't just want to do. So I have no idea. I'm not the best with ideas. So that's AF. And then that's this one, and we also have to set that. So AF is the same as this. CPU.getRegister PSW.setRegister data. Alright, and so now we go back up here. Oh, what's the error? Is it this? It's this. Okay. 0xF5 is the opcode. I'm forgotten. So F5 and it's AF. Okay, so you do this dot push, and then we need to do AF. All right. So now that we have that, we actually need a bunch of breaks here. Let me just do that. So now it basically pushes whatever register I just put in there as the thing into the stack, or wherever the stack is in memory. And we need to do the same thing for the other ones, so BC, DE, and HL. And then we also need to do CDE, C, D, and E. And we can just copy that and pop it instead. So instead of push, pop. Pop, 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 pop. Is this one? I don't know what these opcodes are. It's one. Okay. So 1, 1, 1, and 1. And that should work. I don't know because I don't have the test program to work it, or I don't have enough codes to test it with. So okay. So now we have pop and all these, and now we can actually get to the adding stuff. Yay! So the problem is nobody on my friend in real life believes I can code. I don't want to code something you can show like a 3D game, but I'm a backend developer and I just can't handle lightweight Java game layer 3. Well, I don't think you should start with a 3D game. I mean, that would be really cool to show to your friends, but I don't think if you are a backend developer, I don't think you should start with 3D. what I would recommend is HTML Canvas now, or a game engine that's an actual game engine, like Unity or Game Maker or whatever game engines there are these days. I don't use them, obviously. But if you're starting out with game development, I would recommend a game engine and then go on to like actually coding with libraries and like actual languages instead of just using an engine. So if you want to make a 3D game, you can use Unity. If you want to make a 2D game, you can use Game Maker. I would recommend Game Maker or Unity. I just don't use them because I think I'm not. I think I'm better than that. That's not saying that they're bad game engines. I just think that I really don't. I don't want the crutch of a game engine, and I want to be able to learn these by myself and be able to show off that I can do it by myself. So, however, if you're beginning, I would highly recommend a game engine. Just a little tangent right there. Anyways, so we are probably going to have to do the hard part, which is the math. So we've basically done all 100 loading commands that load stuff to memory addresses and all that. And so now we have to do the math. So now we need to do public void add. And we just need to do string register to add with. And because you only can add with register A, so we can just assume that A is adding one of the registers. So we also need to do a bunch of these. So I know in is reset because that's the subtract flag. We're not subtracting because I don't think we're subtracting with addition. And then we need to say if it's 0, then set the flag to 0. BRB, alright, you can BRB. Set of carry from bit 3, set of carry from bit 7. So I think we can just do that. So yeah, let's add these in there. So this dot set register, and then this is register A with this dot get register of register A, or I need to do int addition is equal to this int addition, this dot register is A, and then plus, is this a signed byte? I don't know if this is a signed byte. Alright, well, Gameboy add CPU instruction. Hello, E-Trade. So I'm just trying to figure out if the add is with a signed byte or an unsigned byte. Signed byte. Alright, so we got the CPU opcode reference. Alright. So I need to do add 8 with a register. So Okay, so N8. Let me look at what that legend means. Oh, there's my mouse. So N8 is just an 8-bit register. And E8 is the sign. Oh, right, so it isn't. Okay. Alright, thank you, whoever that was. It is not a sign byte, so if it's over, so it is between 0 and 255, and that makes my life so much easier. So, int addition, if this is .get register, is this .get register that, plus, well, this .get register, and then whatever is in the register. And so this is what we have to set our flags on. And we can just kind of take this little example right here. And then we can at the end just say addition. And we can say if, so the 0 flag, so if the addition is equal to 0, subtract flag that's already false. So if the carry flag, so if this .get register a or this .addition if this addition is greater than 255, half carry flag, that is going to be a bit more complicated. So that means if addition is greater than 255, and then if this .get register, if this .get register of A is this is kind of hard for the half carry flag. It's like super weird. I don't know why. So if bit 3 goes to bit 4, or if bit 4 is activated when the addition is done, so bit 4 is, what's that, 16? 1, 2. Yeah, so if it's 16, I could say if it's greater than 16, but I mean, if the addition is greater than 16. Sure, let's do it. Addition is greater than 15. Well, it has to be greater than 15 because 0 is counted. That means that just the 5th bit is in. That means that the 5th bit has been activated, or 4th bit technically, because 0, remember. And so, yeah. And then after these flags are set, we just need to say if addition is greater than 255, addition, that's not how you spell addition, addition, doing great, addition minus equals 256. And then that should be add, and that's it. So that is pretty simple. I think I did the half carry flag wrong up there. What was that? Oh, okay, that is a person in my, that is, okay, I am going to Hello, I am back. So just someone in my house that is yelling, and I don't like that because it's kind of on my mic, and so yeah. Anyways, so this is just doing some simple looping if anything bad happens, but yeah, and then that will work for any 8-bit register. So let's add that into our thing. So case, what are the cases? So 8 through 7 and then C6 for some reason. So a 0x87, this dot add, it adds A to A. So I guess you can double what you got. So I guess that's how you can do exponents, yay! So yeah, well, you can do a lot of things with this. It's just that you have to do it's a bit more drawn out. So case 1, 2, 3, 4, 5, 6. So A, B, C, D, E, H, L, and then whatever is at the address of HL. So 6, 5, 4, 3, 2, and 1. And then we have C6, which is just adds the next byte. So 0x. I can't think of any idea. I know it's like sometimes you just want to code, but you don't know what to code. So, I would say make a simple game using only text. Give like sometimes limitation gives you great ideas. Make a simple game using only text. Like try to make a graphical game using only text. Like so, there's a lot of things that anything that has a console can make a text game. So, just think of that. Just text game that is very graphical. I wouldn't say very graphical, but at least has more. It's not a text adventure. I would say a text game with some graphics, and that's a good challenge. I might do that myself one day, but right now I'm doing this. So this dot add, and this adds the in. So there we go. Uh, hmm. So that is all the add, and then add is just add plus the carry flag. It's basically the same thing as the add, except it has carry flag. And then so I say boolean with carry. Probably just do that. Ooh, and now I got something. See, I mean, oh, wrong one. Now just simple restrictions can make some great ideas. And then what I'm gonna do is I'm just gonna have public void add with just the register, and then it's just gonna call this dot add register and then false. And so that fixes that error, and then we can say true. And then this dot register a plus this dot the register it gets, and then plus, and then with carry. Oh, I always add a space there for some reason. If there is a carry, add 1. If there's not a carry, add 0. Oh, and then I have to put that all in parentheses. All right, so now we can say add with carry, and then it's just the same thing, except it's the later half of the 8s. So boom, boom. We just say true. Boom, 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 and boom. And then 8F. Is it 8-8? 8-8, I think. 8-8. or not 8A, 8, 9. 8A, 8B, 8C, 8D, 8E, and then what is it, CE? CE. Yeah. And then subtract with carry and, or, XOR, and compare. Alright, so add with carry. Okay, we already did that. And we did that. So now we need subtraction when subtract with carry. So subtract with carry. Hold on. So Game Boy CPU subtract with carry number opcode. Here we go. It's the same one. All right. So subtract with carry. And this one. And then what's the opcode called though? Like I don't know what the Okay, so to speak over it anyways. So I'm just basically copying and pasting and just changing a few things up. So hopefully it is going to go well for me. I can probably get all the instructions done tonight, and then I can run the code and see if there's any errors. There probably will be, but if there is, we can fix them, and that's the whole point of this. So instead of add, we're going to do and these are kind of way more simpler than the math ones. The adding and subtracting, and the add with carry and subtract with carry, and so now I'm just going to do the same thing, but for OR and XOR. OR. Wait, no, this is the wrong one. I need to do it for AND. So I need to do it for OR. And if you actually look at the CPU manual, it's just the flags are the same except this one. Can we just set this to false? and and so we need to say this to OR, and instead of using the AND, bitwise AND, we need to use bitwise OR, and then store the results, and then use the different variable names. So there we go. It's pretty simple from here on out. It's just, changing a little bit of that one and adding those new opcodes in. So, OR, now we just use OR, and since we really don't have to change anything, we can just do that, and it uses B and F. So B, 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 and then F. So there we go, and so that's and we got OR down. We need to do XOR, which is exclusive OR, which is the caret, or the top caret, or whatever you like to call it. I don't know what it's called, but it's called that. Yeah, I guess. I don't know. It's the one with the upside down V, basically. And its use is the same thing as this one, except, it's called XOR. And every time it says OR, I'm going to replace it with XOR, and instead of using this, I use this. And there we go. And so we go back up here, and we change this OR to be XOR for all those registers. So XOR, 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 and just use A, and then AF, and then all that, and then E, E. This is going to be E as well. D, C, B, A, 9, 8, and then F. Not A, Z. It's going to be A. That's right? D, A. Okay. And so now we need to do compare, and comparing is basically just changing the flags. That's all we're changing. We're not changing anything else but the flags. So, that's pretty easy to do, and I bet, I open up snipping tool, and I bet we use compare for a lot. Oh, we don't. So we use increment, and we probably use decrement, and 16-bit arithmetic, and then miscellaneous, and then we dot. And I'm just trying to see what the rest are. I'm just trying to see what these rest like. So CVs are introduction 1, Right, so let's go back to here. Close that out. So yeah, I'm feeling like we could probably do this for, like we can do this. So now we need to use compare. So public void compare, and this is going to be a register. So register, and this compares A with whatever the register you chose, and so pretty simple. So if the result is 0, and it's basically changing flags. We're not setting any registers, we're just changing flags. So compare. So I'm going to say int compare is equal to this dot get register of A minus this dot get register of whatever the register is. And we can basically just do the same as this. It's really simple. So, but instead of subtraction, we use compare. And so if it's equal to 0, if they're the same, the 0 flag gets set. If it's bigger, the carry flag. If A is bigger than the register, the carry flag gets set. If it isn't, the carry flag does not get set. And so that's how you can tell whether or not a register is bigger, smaller, or equal to register A. And I think that's a really cool way of doing it. So yeah, and then you can say like, going to sleep, bye. Okay, bye, E-Trade. I will see you later, probably when I have another time to stream and you can come see it. So what even is our, wait, what is our difference? So it's 1:30, so it's like 6 hours? It's probably 6 hours, because it's 2:30 for you now. And yeah, so you have, so I mean, if I stream, what if like if I stream it like in the middle of the day, you can probably see it. So anyways, goodbye, E-Trade. So yeah, if I stream at like 12 o'clock, you can see it and you can actually watch it and enjoy it and actually pay attention and not be so tired. So yeah, anyways, so now we're going to increment registers. So this is basically the same as what we're doing, and then see if the result is 0, which I highly doubt it will ever. I mean, unless it's 255, then it will be 0. So anyways, so we're going to do another one, public void increment, and then whatever register it is. Oh, I forgot. See. Anyways, so now we need to actually increment it. So int increment is equal to this dot get register, or this dot get red. We have to set it first. So this dot set register is equal to that, and then we need to set it to this plus 1, and that is how we increment things. Can I convert from void? Oh, and we don't need to. We can do this because we have to do stuff with it, and then we basically do the same thing we do here but for adding. Wrong one. And we just say increment, increment, and increment, and then we just say this dot set register to increment. And this is the same for decrement, except it's subtracting. That's what it is. or if increment is greater than 255. It's basically adding, but the register is 1. So I can actually just copy this, go all the way down to increment, and then just change the first line to 1, and also its register. And boom, there we go. And so decrement, oh, I actually have to add those into our switch case table. So increment is for 3C, 04, OC, well, 04, OC, 14, 1C, 24, then so this one's actually pretty brand new, brand spanking new. So 3C is going to be this dot increment A, and then break 1, 2, 3, 4, 5, 6. Just do 6 for right now. B, C, D, E, H, L, and then whatever the address is at HL. So HL. And then this is all different. So this one's actually going to be, what is this? 3C and then 04. 04. Here C. 1, 4. 1C, 2C, and then it's going to be 3, 4. It's going to be 2, 4. And that's going to be all good. Since you can't really increment the next byte, like I said, or I never said it, but that's what it basically means. And then the only difference is it changes from 4 to 5 and C to D, and it's decrement. And so it's basically subtract, but you can only subtract. So subtract, but only once. Oh crap. Decrement. And then it's going to be just -1. And instead of using just a register, we can use any register. So there we go. Yeah, just a thought. Just a thought. Just some brain candy for you. Actually, really some brain candy. I never said anything. I just did something. I coded something. Unless it's somehow brain candy to you, which I highly doubt it is. But okay, so we got 3, 4, and then we need to actually change this to D, and then 5. D, and 5, D, and 5, D, 5. And that is the increment and decrement. And now we need to do 16-bit arithmetic. This is basically just add all these, okay, and then add the stack pointer to 1 byte signed immediate value. And this is signed, so we have to, it's basically going to be, and then increment and decrement, it's the same thing. Flags affected, none. Decrement, flags affected, none. And then miscellaneous. Alright, alright. Okay, 16-bit. Okay, yeah, we're here. So we need to add in, which is whatever these things are, to this. So I can't really use this type of add because it's only meant for 8-bit adding, so I actually have to see if it got added. So add, nor, XOR, compare, increment, and decrement. I could do, I'm just going to do this. And yeah, I'm just gonna add, so public void add 16. It's just gonna add 16-bit things. So it's gonna add HL, and then it's gonna add SP, and then that's it. So add 16-bit string register 1 string register 2. It's gonna be pretty simple. It's gonna just add. I mean, this is what this does, and then it kind of gets rid of the limitations of adding with such big numbers. Frickin'. So int addition is equal to get their first register, so register 1, and then it gets the second register, which is register 2, and then there's no carry. It's just adds them together. So the carry flag is if it's greater than whatever 64 times 1024 is, 65536. 65536. And then we need to do 32, 32768, 32768. And then if it's ever 0, that's kind of obvious. You don't really need a specific number for that. And then reset the -1, so that's false. And if it is greater than that number, you just subtract that number once again. Wait, actually, it has to be one number less. Forgot. And then subtract that number. So there we go. That is adding 16-bit, and then that actually works for the entire adding 16 bits. It's just that we have to do specific adding 16 bits. So we have to go to here. So we have case 0x09, and this adds 16. It adds HL, and what does it add? It adds, does it add BC, I think? Yeah, it just adds BC, and then we do that 3 times. Let's break it, and then 3 times. Case boom, boom, boom. This is BC, GE, HL, and the stack pointer. And this just is 1, 2, and 3. And then we have to do the same thing, but for the stack pointer. Boom, 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 boom. And where is it? Oh, it can only add. Oh, what is it? Add 16, and then it adds just the next number. Signed number. Oh, crap. Nah. So it adds the next signed number. 1 byte signed immediate value. So it is signed, and it's basically, what is it? Is it? I've done this before. It's this one. It's load HL, except it doesn't load. So it's basically load HL, except it actually happens. Wait, I never even finished that one. Hold on. Load HL. Here. No, let's decrement it. And here we go. No, that's not it either. Is this it? No. Wait. Oh, yeah, 16. It's a 16-bit. Load the... Is it this one? It's this one. Okay, and then we actually have to put that in HL. And I never did that. I just never did that. I just never did that. Wow, that's just kind of stupid of me. And so that is it. And so we need to just say this set register HL to address. And that is actually fixed. And so now I can actually use this to do the add HL or whatever it is called. I need to do public void add stack pointer. It's kind of obvious what it does. And I can actually just do this simple thing where HL is fixed, and that would have broke it right there. But anyways, so there we go. So it gets the next byte, and then it makes it a signed byte, and then it gets the address of that byte, and then it fixes the byte, and then we need to set the stack pointer to that byte. And alright, so that fixes it, and so now I actually got to go up here and fix this problem that I made. It is just I just got rid of this one because this only is used once, and I'm just saving up on parameter space. And then here, this just doesn't have any parameters, and it's just add SP. And what is this called? F8. Wait, no, that ain't it, right? Where is it? Add, oh yeah, here it is. E8, it is E8. So E8. And so that is all of our adding done. I lied. I lied to you. It's not all of our adding done. You gotta do increment and decrement for these values. So I'm just going to take this and increment, and then to increment something, increment 16, and then decrement 16. That's not 16, that's 15. I don't want 16. So with this one, there's no flags affected, which I'm glad of, so we don't have to do any of that complicated stuff. And then the subtraction, if it's less than 0, it adds, what does it add? This big number. Boom, 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 boom. And there we go. So it is actually now fixed, or it is now ready for our new registers, and it is what all the other four, so 0, 3, and then 0B. Alright, easy peasy. So 0x, or case, 0x, 3, 6, is that what it was? What the first one was? 3, oh, 0, 3. 0, 3. And then this just says this increment 16, the BC. And then we gotta break it. And so now with that, we need to do the other 3. But for the other 3 HP and SP, and then this is 1, 2, and 3. 1, 2, and 3. And now with this, but like the same concept, except it's a bit different, we need a decrement. And this is just using B's instead of 3's. And it uses decrement. And that is it for all the math stuff. What? That's not what I wanted. There. Alright, so now that we have all the math stuff, so that's all the math stuff and the loading stuff, that took up a lot of code. Now we have the miscellaneous. So we need to do swap, which swaps the upper and lower ones. It turns off most of the flags. Okay. And this is actually using a new function, or that really uses CB, and I'll get into that later. Right now, we're going in here. Alright, decimal adjust register A. This instruction adjusts register A so that can read correctly. Binary coded decimal is obtained. What is that supposed to mean? I'll get back to that. I have no idea what that means. So I actually have to go down here and actually increment, decrement. Okay, here we go. Public void DAA, and that doesn't use anything, so we just need, I don't know. I know what the next one does, which is, what is it? I forgot already. Complement. Okay, so complement. Oh, I accidentally opened up Discord. No, you don't. Okay, click out. There we go. So it sets the carry flag. The no operation. You gotta. I'm gonna. I'm just trying to read all these. Enables interrupts and disables interrupts. Alright, and then the fun part, rotates and shifts. And I'll actually take a break after I get all these miscellaneous done. Alright, so let's do complement. So complement basically, hey there, I really like this idea and I'm sort of following along with my own touches here and there. I'm also interested if you or will plan to pick back up on the lightweight Java Game Library 3 series. Don't worry, Bruce Cosgrove, I will pick up on the lightweight Java Game Library 3 tutorial series. I said that I would probably release an episode a couple weeks ago. There's a problem with that it was a couple weeks ago, but anyways, so hopefully I actually get around to doing that. I actually have to record me typing that in, but it's been a while since I actually touched that. Like, I don't know, like a week ago, a couple weeks ago. So I have to like refresh my memory on it. It's gonna be about third-person cameras, and then yeah. So anyways, let's continue on. So with this complement, it basically flips up all the bits, which is the simple not san, or bit not san. It's not this not san, it's the san sign. It's this not sign and not this not sign. It's not this not sign, it's this not sign, if you know what I'm saying. I'm just trying to confuse you. We're gonna be using this. So this dot this, what is it gonna be? Complement 0 and care flag, and then the negative. Okay, so we're gonna say int complement is equal to not this dot get register of A. And so we need to do the flag thing, so we can just copy the usual flag routine of set flag. It only sets the subtract flag and the half carry flag. Crap. True. And then we need to just say true, and it turns off the other ones. Or not, it's not affected. It's whatever, it's not affected. So they're not touch actually. Only 2 of them are touched. As you can see, not affected, but the negative, or the subtraction, and the half carry are. And then we can just say this dot set register of A is equal to complement. So there we go. So that is complement right there. Basically flips up all the bits, as you can see, flip all bits. And it's used 2F. And I also should do the other one. So Ooh, why are these like this? No. So anyways, we need to do 27, so case 0x27, and that is this .daa, which is apparently turns to binary coded decimal. So, and I don't know what that does, and so I'm just going to search that up. And then the next one, which is 2a to f. So 2f, and then this is just complement, this just flips all the bits. So, pretty simple. Alright, let's go on to the next one. Which is complement the carry flag, which just inverts the carry flag. And so actually we just do public void complement carry flag, and that obviously just inverts the flag. So CPU dot get register PSF dot set flag, and the carry flag, so PS3 register dot carry flag is equal to, well, CPU dot get, or not CPU dot get register. I don't know how to, my brain's going poop. And regis dot get registered, there it is, dot get flag, and then the carry flag. So this basically just inverts the carry flag, and that is a pretty simple instruction. And in fact, I'm going to do the next one, and that is set carry flag, and that basically is just turning it on. And that is even more simpler than before. So it's set carry flag. All it does is this. It just sets it on. So now what we can do is we can go up here and we can add that into our thing. And those instructions are 3F and 37. So case 0x3F. This is the this dot complement carry flag. Sorry, carry flag. And then for 37, 0x37, what we do is this dot carry, what is it? Or set dot carry set carry flag, and let me break. So those are just a few things. Apparently that was necessary. I don't know how they're necessary, but we're going to see when we emulate this. So this is the no instruction. This is basically if you just want to kill some time. So case is actually going to be the first one because it's actually 0. So 0x00. And it's just going to be this dot not and break. So this is actually not created, and it's public void NOP, and it just does nothing. So there we go, just it does nothing, and it's simple as that. Halt and stop are something that, like all these, like these deal with things outside of the registers. So I'm gonna have to actually create some new variables for that. Or actually I'm gonna create it and then I'm just not gonna do anything with it. So we got halt. So we got public void halt, public void stop, and then public void interrupt, and then boolean on. And right now they're just gonna do nothing. So nothing yet, nothing yet, and nothing yet. And I have to go down here and say all these cases Let me just find that again. Yeah, that's the only one. So halt is opcode 76. So case 76 0x76. This dot halt, and then breaks, and then case 0x10. This dot, what is it? Stop. And also break, and I forgot to put a semicolon there. So now we also need F3 and FB. So case 0x F3, this dot interrupt, and it's going to be turned off, so false, and it breaks it. Case 0x F6, and it turns it on, so and these are the miscellaneous. Right now they don't do anything, like most of them don't even do anything. To be case, wait, it's not F6, oh, it's FB. FB. So most of them don't really do anything right now. All they do is just nothing. They just increment the program counter, which will cause bugs. But no, right, I don't really care about them right now. So, anyways, so yeah, now we got those miscellaneous. What we need to do is right here. So we have to do some rotates and shifts. Most okay, so I'm telling you that some of them are going to be normal opcodes, as you can see, normal opcode, but some of them are going to be using a new type of concept, which is CB. And CB is a way of creating more opcodes. So they have designated that CB allows for more opcodes. So we have rotate whatever register to the left, and then the old bit goes to the carry flag. And then same here, but it actually rotates through the carry flag, aka it puts whatever was in the carry flag in the first bit, and then the carry flag now contains the old bit set data. And then right old bit, and then right old bit goes to carry flag, and then through the carry flag, and then shift in left to the into carry, and then least significant bit of in is set to 0, and then shift right into carry, and the most significant bit. Most significant bit doesn't change. So, and that's all CB. Shift right into carry, most significant bit is 0, and bit opcodes, which just test each bit. So bit. It's just looking at the rest of the bit codes. Alright, well, I thought I'm actually going to be stopping it right there for today. We've added a whole bunch of bit codes. Let's see if we can run anything. So let's go to the Game Boy. As you can see, we have not added all of them because I know there's probably there's a CB right there. CB is right there, and there's also CB right there, CB right there. Those are just those are just bit shifting. So what we're going to probably do is going to say while true CPU.clock. Okay, let's see what errors come out. And we can't really do any of this. And not really any errors, so I'd say it's pretty good. you can't really debug anything. I mean, we'd have to go through I mean, yeah, we can do this system.out.print, and then it's going to print register A is equal to, and then plus CPU dot get get register PSW dot get register A, and then plus comma, and then some white space, and then we just do that for the rest of the registers. 1 2 1 2. So we have F B C D E H L. We need the program counter, and we need the stack pointer. Program counter, stack pointer. Here's a tip: you can type S out and then control space and already fill out. Oh man, that's a really good tip. That's actually is very helpful. I wish I knew that. Thank you for telling me. Get status flags. Then we have to say get register BC. We gotta say that there for that there. So register DE. Boom, and then register HL. And then we don't need any registers here. Just say get program counter and get stack pointer. And then dot get stack pointer. And then this will get 1 2 1 2 1 2. And for the stack pointer, we don't need this comma because it's the end of it. All right, so actually, so now that we have this test, I was just seeing if this would work, and it did. So let's actually let's do that test actually. And so as you can see, it's doing great right now. And there's nothing really different, which I thought there would be. Also, it just went really fast. What is the program counter? CPU program counter is that, so I'll just put it as 0. It's probably going to be an error. Stop. There's actually some numbers in there. Holy crap. Look at this. Look at this. So the stack pointer is 0 to 55. I don't know if any of these are wrong. So I can't really prove anything. Oh, well, that's something that's not right. Well, stack pointer also has an extra 0 on the front. I don't know why. So yeah, what is that first? I'm actually going to print the opcode. Where is it? CPU.clock. I'm actually going to try that out. Control print. Control space. Control space. Do I have to actually do it on here? Oh shoot, yeah I do. That's actually really cool. Whoa. Oh, we're already printing out the opcode, but integer dot to hex string opcode. And so that's already ruined. The problem is that's going so fast I can't really stop it, so alright, well, I mean, I think I'm going to try to like slow it down to where it only goes one. I move it, but there's going to be some weird input. I just too slow. There we go. I think I stopped it. So FE. Let me try to read what the program actually says. Alright, so 31. Okay, so 31 opcodes is 31. That is set the stack pointer to the next two things. So that is FF and FF, or FA and FF. And it looks like it didn't do that. Looks like the stack pointer's off. So load register to registered, stack pointer to NN. So register to register, set it to, then get registered. So what is NN? Looks like getting NN is wrong. NN, FEFF, where is? Here we go. So it gets the least one and gets the most, and then it converts it. Wait, CPU dot this dot get next. That's not what I want. That kind of ruined the command. All right. Well, like that kind of ruined it as well. Just two. Did I do it? I did it. All right. So here we are. So it sets the stack pointer to. Okay, I'm going to put these into hexadecimal numbers because that makes the most sense. Main. No, it's in Game Boy. Game Boy. I'm just going to do public static string to hex, and that's going to be the int value, and it's just going to say return value or integer dot to hex string value. Now I know that's just kind of stupid, but it just makes it much more simpler to do. So just say utils dot, that's utils, not untils, utils dot to hex, and then dot get status flags, and I gotta do the same thing here. So utils dot to hex, and there we go. So boom, 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 boom. So BC, and this gives me DE, DE, HL, HL, and then it gives me 2, 2, 2, and utils.2 hex. So there we go, and then finally, and the last one I forgot, we actually have to, okay, so that prints the line. We should probably, after we do this, there we go. Yeah, we still need to do the system.out.print and just line, because I'm too lazy to put in. I didn't do it in time. Yeah, I didn't do it in time. Nope, still didn't do it in time. That is some good timing. I did not do it in time, no. Okay, that's some good timing. Nope. Okay, I guess that's good enough. Alright, so let's check it out. Okay, so the first command is to load the stack pointer with the two next bits with the first least significant bit with FE. And so it uses FFFE, which is correct. And then we have to go to AF, which I have no idea what that does because I'm choosing this. So AF. Oh, that's 0x AF. 0x AF. So that XORs A with A. Something about that doesn't seem right, but okay. Hold on, let me just read. Okay. Game Boy boot ROM disassemble. Here we go. Always on here. Okay. So it loads the, yeah, okay, so we have to, it loads the stack pointer with FFFE, with FFFE, XORs A, and so that's correct. And then it loads load HL with 9FFF. So apparently register L is using the wrong one. Yeah, it's not right. So hold on. So yeah, register L is only supposed to be 8-bit and it's 16-bit, and that is not correct. So I'm trying to think. Okay, so yeah, and then 4 XORs it, and then so we have 9F and then 9FFF, and that's not right. So opcodes is something to do with HL. So HL. Probably something to do with the register pair if it's that basic. Yeah, that's not good. So it's got to be and XF FF, not FF, like that. All right, let's try that. Nope. Nope. Oh no, I didn't. Yeah, I didn't. Nope. 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 This is kind of stupid how I have to do it like this. I like have to wait. Nope. Wait, is it? No. It's so fast that I can't do it in time. There we go. Alright, so I have done it now. Alright, so it loads HL with 9 FFF, so 9 FFF it's loaded. And then it decrements HL and A. So it stores whatever is in A and whatever is in address HL, which is FFFE, and then decrements it to F9FFE. So that's right. And then I don't have those functions yet. And then set up audio. So it loads H. So it loads HL with FF26. So FF26 at program counter F. It's probably I know that's an error because these aren't in and it doesn't correctly read the program counter. So then it loads C with 11. So C is now 11. And then it loads A with 80. So A is now 80. So I feel like it's doing good. So I'm just done testing it for now. I'm gonna add the next instructions probably tomorrow. I'll be live streaming tomorrow if you don't know. And yeah, so I will see you guys later. Bye.